Oops, recording. Okay, let's just start with energy. And this is part 1. And let's just explore energy from a very qualitative stance. Okay, so how would you define energy? What is it? What is energy? Yeah, Justin. The ability to do work. Okay, it's classic definition.
This is true. But isn't that just
Okay. Now that's an issue because what does it mean to do work? What is work?
motion?
Motion. That's not really enough information. What else? Yeah.
Like the ability to put a force or exert force on anything else.
Okay. So let me ask you this question. The lights, would you say that they have energy and use energy? Are they applying a force on anything? Is anything moving in the lights? Lights moving. How about my computer? My laptop uses electricity, has a battery, uses energy. We would qualitatively, colloquially say, yeah, this is using up energy. What's moving? There's
The fans on the
okay, so you have electrons maybe moving around. Maybe there's the fans, some mechanical things, but not all mechanical things. So energy is not necessarily a mechanical feature, right? There's a little more to it. So when we say it's the ability to do work, this is kind of limited to mechanical energy. But I want a more general sense of energy. Because we can use energy to do things more than just work, more than just move and lift and, whatever, turn, whatever it is, right? There's more to it. Yep.
The ability to enact a change.
Enact a change. That's a little more general, and I like that. Ability. How about ability to cause change? I like that. Ability to cause change. An object with no energy is inert or inanimate or something along those lines, right? Cool. Any other thoughts about energy? What else can we add to energy? So as I go through this, again, I am really looking for a personal explanation, right? I don't want the textbook definition, ability to do work. It needs to be something that is, Yeah, it seems kind of weird sometimes when I think about how I understand physics. Just having done physics for so long between aerospace engineering and this is like, it really is both a visual thing in my mind's eye for every concept of physics that I deal with, that I've become so familiar with, that you kind of envision it. And also, it just invokes a certain feeling. It's like, when you've done something for so long, you don't think about how you do it. You just know. It's like when you play piano, the first time you play piano, you're like, okay, where's middle C? And then you kind of like work your way, and you gotta learn your scales and so on and so forth. But if you do it enough, you just know, right? Or tennis, and you're not thinking about how you're doing your angles. You just know. You just know how to do topspin. You just know how to do backspin, right? So it's kind of the same thing. So what I'm looking for is your gut feeling at the moment about what energy is, right? So try and envision how energy is often described in just day-to-day terms. All right. So if you take that, then what kinds of energy do we have? Just as we can categorize different forces into normal force, friction, tension, so on and so forth, we can also categorize energy. So Nathan.
Like mechanical, electrical, chemical.
Okay. mechanical, electrical, chemical. What else? Yep. Potential. Interesting. This is going to be a bit of a web. See, because you can talk about an electric potential energy. You can talk about a chemical potential energy. What else?
Wasn't it gravitational?
Okay, gravitational potential energy. Gravitational. And see, gravitational can be both a mechanical energy and also a potential energy. It's mechanical in the sense that when you talk about mechanical energy is usually associated with the bulk object. Okay, a macroscopic kind of energy. So gravitational potential energy, you lift something up, it now has gravitational potential energy, as opposed to chemical energy. Chemical energy is in the electrons, it's in the bonds. It's not really macroscopic. You wouldn't talk about the chemical energy of my laptop or something like that. I don't know. It's kind of weird. Yeah. Thermal energy. That one really is kind of on its own, I would say, but we'll see. Thermal energy, what else? What's nuclear energy? Okay. Nuclear. Go
Where
ahead.
does that come from? Like, why is that a thing?
It's just people just say that. Yeah, Akash.
Southern white people.
Kinetic. Cool. Kinetic energy. Okay, kinetic energy is another form of mechanical energy. What else? Yeah.
Rotational energy?
Rotational energy, that would probably fall under kinetic energy because it's still an energy of motion, right? A bulk motion. What else? Was that? Yeah, Nikhil? Elastic? Good. Okay, elastic energy is another form of mechanical energy. It's usually stored in the bulk. A strain. Thrust? I wouldn't consider thrust an energy because when you create thrust is a force which is applying. Yeah. What else? Keep thinking. I would say there's at least two others that are not. Yep, Keizo. They're different. Magnetic or electromagnetic? Which one? One of them? Okay. So, electromagnetic energy would be like what? Someone give me an example of electromagnetic energy. That. Light, right? I'm talking about light. So, X-rays, ultraviolet rays, light waves, so on and so forth. So, electromagnetic. I'm gonna put /light. Right. When we talk about light, talk about electromagnetic energy. Cool. Anything else? So many subtle things that permeate our universe that we don't ever really realize that they're dark energy. How about we put things we understand first?
The force.
The force, life energy, the soul, organic energy. I would also put that in the realm of things we don't understand. Nah, at least not scientific.
We're gonna feel so stupid when we finally die.
How about this? how do you hear what I'm saying?
Sound.
Sound, right? Sound is different.
Light.
Because, yeah, wave energy is different from, it's a little different from electromagnetic, because electromagnetic is not mechanical. Electromagnetic permeates space in a vacuum. Waves are different, though. Sound waves, pressure waves, ocean waves, there's an energy associated with that kind of motion, and yet it's not really the same as kinetic energy, because it's not a translation of a material, right? When I speak, I'm not shooting air molecules out of my mouth into your ear. That's not how it works, right? So, whoops.
More or less.
So we have wave energy, which is also mechanical. I would argue that elastic energy is also usually a potential energy. You store energy by stretching and bending something. Yeah, or compressing. I think that's pretty comprehensive. Yeah, I mean, I think you could throw other things in here, maybe like. I mean, this is pretty good. Well, I'll put it this way: things that are elastic. Elastic energy, you can define it in such a way that it wouldn't really fit in any other category. Same thing with kinetic, same thing with electromagnetic. They really are pretty distinct from everything else, right? Okay, so let's go ahead and just define a handful of these. So start with the easiest one, kinetic energy. What is kinetic energy? Sure. Gosh.
Energy of motion.
Energy of motion, perfect. Okay, if something is moving, there's energy with that. Okay. Now, generally, kinetic energy is associated with a macroscopic scale movement. Okay, so you have a car, a bus, a phone, whatever. It's moving. It has, the object has kinetic energy. You wouldn't usually talk about the kinetic energy of like. Well, I mean, I guess you can for like a beta particle or something like that, but usually we talk about kinetic energy of some bulk object. How about I think this is relevant. How about thermal? What is thermal energy then? This is one that many students tend to struggle with. Microscopic motion. Okay, we'll build off of that, Akash.
Is it like the energy retained within a certain surface?
Not necessarily a surface, but an object.
The speed at which particles move, very small particles.
That's difficult to answer.
Isn't it the point?
Well, hold on. Let's do one at a time. Okay, so Morgan said kind of the microscopic motion, and Akash said it's kind of the internal energy of an object. And they're not really far off from each other, because if you look at any material, like a solid or a liquid or a gas, at the microscopic scale, the atoms and molecules are always moving just a little bit, right? The idea behind absolute zero is something is at 0 degrees Kelvin, right? 0 Kelvin means that it has absolutely no motion anymore. And that is theoretically an impossible physical state, right? So all objects are always moving a little bit, all molecules. And that's what thermal energy is a measure of. It is the microscopic vibration, if it's a solid, and if you think about like a metal and you heat it up, as you heat it up more and more, why does it start to become more amorphous? Why does it turn into a liquid? It's because the individual particles start having enough vibrational or motional energy to overcome the bonds that keep it in its lattice structure, right? So they start to move around. So it is the average random, and it's important to note that is the random. It's the random motional energy at the molecular level. Okay, so like if I have a gust of wind, it's a bunch of gas that's moving, but that's not really its thermal energy. That's a bulk energy, right? That is a group, an organized motion of molecules. Within that wind gust, they're still bouncing around with a random amount of energy, and that is how we measure temperature, right? Something that is 100 degrees Celsius compared to something that's at 80 degrees Celsius has a higher random energy, random motion than the lower temperature one. Okay, cool. Let's go ahead and hit up let's do all the potential energy stuff. Okay, so how about chemical potential? Kind of doing these in a little bit of random order. But how about chemical potential? So what's chemical potential energy? Yep. Energy of bonds. Okay, either creating bonds or destroying bonds. What is a bond?
Isn't it like sharing of like electrons?
Sharing of electrons, some sort of interaction involving electrons. At the end of the day, when we talk about a chemical reaction, it is a interaction between elements through their electrons, right? Not through their protons, not through their neutrons, not through their nucleus, but it is a rearrangement of their electron structure, right? If you think about the octet rule and so on and so forth, really all it's saying is that electrons have different energy states, and that they tend to favor lower energy states, and so that when they interact with other elements and they drop to a lower energy state, they release that energy, right? So, or it takes energy to put it into a less stable state or something like that. So, at the end of the day, let's see, it is the energy in the rearranging of electrons between atoms. Right? When we talk about chemical bonds, that's really what we're talking about, is this rearranging of electrons. Either they change whatever change it is. If you talk about a covalent bond and they're kind of shared, or you talk about an ionic bond where it's stripped, either way, you still have a different arrangement of electrons. Cool. What other ones do we have? We have, let's do elastic. How about elastic potential? What is elastic potential energy? How would you describe that?
Restorative.
Restorative, why?
Because it wants to go back to its original shape.
Okay, so that means it must have changed its shape, right? So is the energy stored. There's a specific word for when an object changes shape. We call it strain. If an object there's a stress-strain curve that you can look at where you look at how much force it takes to cause an object to change shape and by how much, and there's a kind of strain energy associated with how much it's changing shape. So energy stored in the strain. And in case you can't remember that word, we'll say the deformation. Okay, strain or deformation of an object. Although it's also important, of an object that can return to its original shape. In other words, if I take silly putty and I strain it, there's no strain, there's no elastic energy associated with it. Yeah.
Wondering if there's don't all objects have some limit of where they're elastic, and then once they reach that limit, it just starts, they lose their elasticity. The rubber band, if you push it too far, it'll just snap.
It's true. What you're Now, it's more like for every different kind of material, they have pretty common behaviors in the way they strain, the way they change shape, and how much force it takes for them to do that. And then they have different behaviors as you push it too far or push it not far enough. Like even for metal, like if you pull or push on or bend metal for long range, it has a very linear behavior of how much it bends. And then once you go beyond that, it becomes really, really stiff. No, sorry, the other way around. It starts to turn it, stretch non-linearly, stretch more than it would normally, and then it'll just break, right? It's true. They have different behaviors along the way, but I don't say that every material necessarily has that kind of behavior. For example, if you look at glass, certain kinds of glass maybe, but you can definitely find ceramics where they don't deform at all. They just can't really deform at all, or else they'll just break because of the way their structure is. They just crack, right? And so I wouldn't consider that really elastic potential energy. I think you can still argue there is strain energy in that, but it's not really the way we would view this kind of elastic potential energy. Usually when we think of this elastic potential energy, we're thinking of the kind where you have very noticeable changes in shape and it kind of comes back. Okay, so chemical potential, elastic potential. How about gravitational potential? How would you describe a gravitational potential energy?
Gravitational potential is
Gravitational potential energy. Potential. Yeah.
Isn't it kind of like elastic potential where the distance is a function of how much energy is stored in the object?
Okay, so the distance relative to where for gravitational?
The larger mass?
Yeah.
Whatever frame of reference you
Sure. So generally speaking, the more far apart the objects are, the more gravitational potential energy you have, and then the closer together, the less gravitational potential energy you have, right? So in other words, I lift my pen up away from the Earth, it wants to fall back towards the Earth, so by lifting it, I'm increasing that potential energy, and then it releases it on its way down. Right?
What
So,
if you exit the Earth's gravitational pull?
Well, that's kind of an interesting way to think about it. There are some pretty interesting discussions you can have about how far gravity can reach. And that is almost borderline like existential kind of a question. Because if you think about the Big Bang, right, the question is, was there an object that was flung so hard out by the Big Bang that it will never be able to come back ever again because it is, you know what I mean? Is there a limit to gravity's reach? Mathematically, no. Right? Mathematically, even the furthest guy, eventually it will pull on it. But, well, I'll put it this way. Classical gravity, like Newtonian gravity, says that there's no limit. Einstein's gravity is different. Einstein's gravity, I don't really know. I'm not familiar enough with it, but Einstein's gravity says that not only was it shot out really far away, but the space, like what we consider empty space, was also stretched out and is continually stretching out. That is the acceleration of the universe accelerating out, because literally the empty space, the fabric of space-time has energy in it and is being pushed out. It's kind of weird. Classically, no. Okay. In most cases, eventually, it will be pulled back in.
What a wild ride.
Yeah. Actually, I take that back. I guess you could have enough energy that you could exceed. That is actually what we call escape velocity now that I think about it. That's different. We'll come back to that. That's an interesting question. I think I misspoke, to be honest. We'll come back. When we do universal gravitation, we can talk about that. I think I was thinking of something else in terms of that.
I definitely think it's an important enough question. Where do you think the Death Star's center of gravity is?
Where the Death
Yeah, because,
Star's
like, in
center
the
of
Death
gravity?
Star, everybody's like always standing up like this. So like even if they're at the bottom of the Death Star, they're still like their feet are still to the bottom of the Death Star, right? And wouldn't they be gravity towards the middle of it?
Well,
I'm pretty sure they're all facing like.
But like in the Lego models, they're all facing the
Oh.
same direction. So I just
Yeah.
think it's-
Well,
it's
that's a
directly
Lego model.
centered.
Anyway, in the Lego model, anyway. Okay, so gravitational potential energy. Let's try and get a definition for it. How will we define gravitational potential energy? Not so much whether you're influenced by it, whatever, but okay. So we talk about it relating to how far away the objects are. That is important. But how do you want to define it? What is it?
What a pain.
Sure, Akash.
The energy and the distance between two masses.
That was a pain.
See, I think it's very interesting because when you think of all of these other energies, it's very easy to see where the energy is. When you talk about kinetic energy, it's in the object that's moving. When you talk about thermal energy, it's in the particles that are vibrating, flying around. When you talk about chemical potential energy, it's in the electrons that are changing state. And elastic potential energy, it's in the thing that's being stretched or compressed. Where is the gravitational potential energy? Because you can't have gravity without having two things at the same time. You know what I mean? You can't have gravity on a person without having the person there. And you can't have gravity without, the earth. You have to have both things. It is. It kind of is. It is really the energy of the gravity that is connecting the two together. Okay, so I think that's kind of an extreme way of defining it, but I just put it this way: it is an energy associated. Okay, I'm kind of giving myself some leeway or wiggle room by saying associated. Okay, associated with the separation of two objects influencing each other by gravity. Okay. And an energy associated with the separation of two objects influencing each other by gravity. So, more simply speaking, when you're looking at the surface of the Earth, it's pretty much the vertical position, right? The higher up it is, the more gravitational potential energy. But it's weird because the energy, we would say, is kind of like in the object, but it's not really in the object. It's because the Earth is pulling it down that the energy comes back. So it's like it's in the connection, and you will kind of see that later on when we start describing gravity in a different way. We start talking about a gravitational field. We kind of describe the energy being stored in the field. That ends up being a much more elegant way of describing where the energy is, instead of saying that the energy is in the object itself. Okay, let's continue on. Let's talk about electric potential energy. So what is electric potential energy? Not electrical energy itself, not the flow of electrons, but what would electric potential energy be?
It's like, when you have a battery, you have that little aluminum foil that differentiates like
almost
the
like
electrons
potential energy.
outside. It's like, that's electric potential.
But what is it doing when you have that battery?
I don't know.
It's a difference in charge.
Difference in charge. Close. Difference in charge. Maybe like an imbalance in charge or a separation of charge. Let's add to that, Akash.
I was gonna guess it was like some kind of, it's like charge, basically, it's like the pressure difference, it's kind of.
Okay, so it definitely has to do with the charge, right? So if you look at like lightning, right? What causes lightning is you have a sufficient imbalance of charge that the electrons are so attracted to the exposed protons or whatever, the exposed positive charge, that they break down the air and create a path, and they go. So it really is, when we talk about electric potential energy, is by creating a separation of charge that they want to come back together, then that releases the energy. So energy stored in the separation of charges.
We can't see the bottom of the page.
Okay. There are definitely some other ones on here. We haven't really talked about electromagnetic or nuclear or wave. We will get to electromagnetic and wave later in the year. Among some of these other ones as well. Nuclear we don't really hit up, but I think at least for now, I'll be honest, some of these you're not really going to see on the AP exam. Not for AP Physics, the C exam. We deal with elastic, we deal with gravitational, we deal with electric potential. We don't really deal with thermal, we don't really deal with chemical potential, but I think it's worth the time to, since we're talking about energy, to look at the fact that these all, whether it's mechanical with like kinetic and elastic, like this physical thing, that energy is the same, measured the same way as these very radically different seeming kinds of energy, like thermal or chemical. Okay, they're all measured and transform and change place, or change from object to object, the same way, or not the same way. They're not different stuff. It's so hard to explain. It's kind of like you have all the different elements of the periodic table, but they all use protons and neutrons and electrons. It's kind of the same thing. You have all these different forms of energy, but it's still just energy. Okay, you can take 20 joules of thermal energy and turn it into 20 joules of kinetic energy. You can take 20 joules of kinetic energy and turn it into 20 joules of chemical potential energy. You can change from one form to another, which leads me to my next point. And so I'm going to move on a little bit from the different types of energy. Really, I want to explore this just to kind of get you guys thinking about the energy around you, especially since your generation is probably the generation that will have to deal with energy the most. It'll be a very important issue in your lifetime, whether you choose to believe it or not. So, it's good to be savvy about these things. So, when we talk about energy and how it changes places and so on and so forth, first let's talk about how it's measured. Energy is measured in joules, Joules. That's how you pronounce it, joules. Like bejeweled, joules. But it's Joules. Okay, Joules. That is the standard international unit of measurement for energy. In the United States, we measure it with calories. Sometimes in chemistry, calories are also used for energy in the SI system. But I think usually you use joules. Joules is the preferred unit of measurement.
Is a joule or a calorie bigger?
I believe calories are bigger. Right?
Depends on which calorie.
The little calorie, I think, is still... I don't know. For some reason, the number in my head is like 4.18 or something joules per calorie. Maybe it's the other way around. I don't remember. But they're both measures of energy. Sometimes, if you ever, for whatever reason in engineering, you'll also see the unit of measurement BTU. So calories. There's also the BTU, which is the British thermal unit. I'm not really sure how it converts either. What's that?
Isn't British thermal unit like the amount of
yeah, it's something weird. There's all these weird Western units of measurement. Yeah, I don't know. So calories are a unit of energy, BTUs are a unit of energy, joules are the primary unit of energy. What's that? Joules are bigger? Okay, so then it's probably the other way around. There's probably like, wait, 0.23. Yeah, so there's probably 4.18 calories per joule. Yeah, something like that. Okay, so so 1 joule is equal to 1 Newton meter. So 1 joule is enough energy to push an object, push with 1 Newton, 1 meter. Or, yeah, 1 joule will be able to push with 1 Newton over at 1 meter. Or you can also say it's 1 kilogram meter squared per second squared. You'll notice that a Newton meter was also used for torque. You'll never describe torque with joules. No, nothing. So you have to look at the context. Okay, you always have to look at the context. If you're talking about turning, spinning, twisting things, it's probably torque, right? If you're talking about any sort of, well, usually you'll just have to say energy, kinetic energy, potential energy. Then that's going to be in joules. Okay. All right. So when we talk about energy and we start quantifying energy, a very good way of thinking about how energy moves around is going to be with this model. Just going to draw a diagram. You have your environment, and then you have your system. Pretty simple. This isn't a real physical thing. It's just a way of describing how you model energy and where it is and where it's going, right? So if you have any sort of energy transfer, so I'm going to put energy transfer with a question mark. Sometimes you have energy transfer into your system, sometimes you have it transfer out. The idea is your system is whatever it is that you're taking into consideration. So this is a very useful way of analyzing scenarios in engineering. So for example, like in aerospace engineering, when we look at our turbine engines, sometimes we're interested in the compressor part. So our compressor is our system, and we're looking at how mass or matter flows into our system and out of our system. Into our compressor, out of our compressor. How is the pressure changing? How is the energy being put in? How is it being pulled out? Right. So a compressor, the compressor puts energy into the system. Okay. Your compressor, what it does is it squeezes the air, which by squeezing the air, you have to put energy into driving those compressors to force the air to get smaller, and then you feed the air into your ignition chamber or whatever, your combustion chamber, and you spray a little fuel in there, you ignite it, you increase the temperature, you shoot the temperature up really high, and then you run it through a turbine. And a turbine is where you actually extract energy. Energy is actually extracted out of the turbine. It's like a reverse fan, so that it takes your hot combusted kind of high pressure air, forces your turbine to turn, and that turbine is connected to your compressor. So actually your turbine, as it's turning, turns your compressor, which feeds more stuff in, and it's the cycle. It's the Brayton cycle. And then you run that air into a nozzle, and then you accelerate it out. So it's nice to be able to look at these as systems. When is energy going in? When is it going out? You want to do that because then you can analyze, like, well, how much energy am I putting in for how much energy I'm getting out? Is it efficient? Can I compare them? I look for a ratio, and I can do all these things for analyzing how my system is behaving relative to an environment. It may seem kind of like, well, duh, of course you have to do it that way, but there's a couple things to take into account when you look at your system versus your environment. Generally, we assume the environment to be this infinite reservoir that has infinite energy and can remove infinite energy. It has no limit, right? Because we're just not concerned with how the environment is behaving. We are only interested in how the system is interacting, really like at this boundary, right? So, what that lets us say then is, how does this energy transfer influence my, the energy in my system? I can now start thinking about energy within versus energy, without, and that helps us with our definition of the law of conservation of energy. So just like with conservation of momentum, we said that if there are no external forces, right? If there are no external forces, the momentum of my system should stay the same. It's really the same idea. If there's no external influences of energy, no energy coming in, no energy being taken out, then the energy of my system should stay the same. So, if no energy transfers in or out of the system, the energy in the system must be constant. Okay. Now the book probably has a little bit of a different definition. The most common definition of conservation of energy is that energy cannot be created or destroyed. I think that's not as useful as this kind of definition, because here's where this definition is most applicable. A lot of times in day-to-day life, and kind of a misconception that most people have who are not educated in this, is that when we use up energy, it is gone. Like my laptop runs out of batteries, it used up the battery, the energy that was in the battery is gone. But that implies that it was destroyed, right? But that's not the case. What this is saying is that if this was an isolated system, it would contain all that energy. And if all that energy is gone, by necessity, that energy must have transferred out. So how does it transfer out? Where does the energy go? Heat. Main thing, mechanical. You have any sort of spinning gears or whatever. Most laptops don't have CD drives anymore, but yeah, a lot of it is heat. Okay, a lot of it is heat, especially for computers or phones or iPads and so on and so forth. Any kind of processing unit that is, your CPU is essentially just rearranging electrons on different parts of your device. That releases heat. Okay, moving electrons releases heat, and then it gets hot, and then that heat or that thermal energy is just dissipated. Right? There's a heat sink in most computers or so on and so forth. Right? The energy is just dissipated. It's also given off as light. Right? You have your screen, you have your speaker. Your speaker's a little diaphragm that's shaking back and forth. Right? That uses up. Or that, I'm not saying it uses up energy. It's transforming energy, which then gets dissipated and transfers out. Yeah.
So you said that the environment, usually assumed that the environment doesn't transfer any energy into the system?
No, I'm saying that if the environment does not transfer energy into or out of the system, then it must stay constant.
Okay.
Yeah. So as long as no energy is transferred in or out, then the system must have a constant amount of energy. Yeah. And so what I'm saying is a lot of times we see a system lose energy and it would appear that it's destroying energy, but what it really is it's transferring it out in a mode that we're not really aware of. Right? Yeah.
Wouldn't, if the same amount of energy goes into the system as out of the system, wouldn't energy still be conserved?
Yeah, you can do that too. And you can have that kind of steady flow as well. This isn't exclusive, right? This isn't the only way to have constant energy. It's just saying that if nothing's going in or out, if you have an isolated system, it cannot change the energy that it already has. It can transform it into less useful energy, which is often the case. Heat is usually the least useful energy that we have, form of energy. because there are ways to transform heat back into useful energy, it's just very difficult. So for example, basically any coal plant is a very controlled explosion, right? Right? Any natural gas, whatever, it's a controlled explosion. Takes all the energy from the chemical potential, converting into thermal energy to boil some water, and then the boil water turns into steam. You direct the steam into a tube so that it becomes kinetic energy, and then that's how we extract it. We extract it with a turbine, right? Okay, moving on. Any questions about just having a good big picture view of energy? Like I said, this is very qualitative, but I think it's important, especially this concept. This concept is very qualitative. When we approach it quantitatively, it's very easy to lose track of the meaning of all the numbers that are going on. You have 10 joules minus 10 joules is equals 0 joules. It's just numbers, but you want to have a good I don't know, instinct about what's going on. So this is kind of, well, all right. So, okay, now let's look at it mathematically. Okay, so if you've been kind of falling asleep in the last 30 minutes, I understand that. You probably saw this like, Mr. Mac, I learned this stuff in like 3rd grade. I get it. I just bring it up again because we're hitting this unit. It's important to make sure that no one is like, has any misconceptions, because a lot of people do, especially thermal energy. You'll be surprised how many people, if you go ask someone who probably isn't in the engineering field, right? And you ask them, what does temperature measure? They'll probably tell you, well, it tells you how hot or cold something is. And then you say, well, how do you determine how hot or something cold something is? Then, they're going to lead you to the explanation of heat. And heat is not a good explanation for temperature, actually. Heat is a transfer of energy. Something feels like these two can be the same temperature because they've been sitting in the room this whole time, but this will feel colder than this one, right? They have the same temperature, but this feels colder. It transfers heat out of my hand faster than the book. It has a higher heat conductivity because it's metal. But if I told you they're both, whatever, 68 degrees or 70 degrees Fahrenheit, how do you explain that thing, right? So a lot of people have those misconceptions. And hopefully you don't have those misconceptions anymore, but you might still. And that's why we study these things. All right, let's look at the math. Okay, so the reason I want you guys to try and wake up is because the math part here is pretty complex. We're going to need to do some calc. My understanding is now we can actually have some fun with calc because you guys know derivatives now. You guys know product rule, quotient rule. Actually, I'm kind of curious because up until now, my last at least 12 years of my life, calc has been defined by Warner.
Oh yeah.
By Mr. Warner. So I'm really curious. I'm really curious to see if Calc AB people, how did you guys learn the quotient rule? Did they use the Hody high minus Heidi ho equal O over ho ho? Okay, that's what you need to know. Okay, that is like the thing. That's how you learn calc. Okay. Anecdotes aside, we got about 18 minutes to go. In order to talk about energy from a mathematical perspective, we need to talk about work, and we need to define work. Earlier, someone said it's the ability to do work. Let's actually define it in a very mathematical way. To do this, we're going to start with Newton's second law. Start with Newton's second law. The net force gives you the mass times the actual acceleration of your object, right? We want to relate to the velocity more so than the acceleration. The velocity is going to give us a little more information, so we're gonna write it in terms of the definition of acceleration. The definition of acceleration is the rate of change of velocity with respect to time. Okay. Now, when we did this and we integrated both sides and so on and so forth, that's how we got momentum, right? We moved the dt over and we integrated with respect to time, and we found that if you look at the contribution of a force over time and you add it all up, right, you get the change in the momentum. You get the change in this value mv, and we call it mv momentum. Instead of doing it with respect to time, what I want to do now is do it with respect to position. Because if I push on something and I actually cause it to accelerate, it should change place. And as it changes place, I will find that there's a relationship between where it is at and how fast it's going. Not just how long I've been pushing it and how fast it's going. So to do that, I'm going to use the chain rule. And I'm going to do this. Take a look at that, make sure you understand why that's the chain rule. You guys see the chain rule in this? Okay. So instead of dv dt, I have dv dx, dx dt. That's the chain. The dx is on the denominator, is now on the numerator, so that when you put them together, you have dv over dt.
That's like the definition of chain.
That is pretty much the definition of chain rule.
I guess the definition of chain rule times mass.
Times mass. Okay, so that's this part. Okay, so again, your job in here is not really so much the calculation of the chain rule. It's actually more important that you understand the meaning of the chain rule. What we're trying to do here is, instead of looking at how velocity changes with respect to changes in time, what we're saying is, how does velocity change with my changes in position? And in order to determine that, I have to take into account that my position is also changing with time, right? In other words, the equivalence here is that my changes in velocity with respect to time are equal to this product of changes in velocity with respect to position, and then changes in position with respect to time. Okay, that is really what is the interpretation of this. Notice here that this dx dt is actually just velocity. So I can write this like this. And now I have changed my derivative to being an investigation of changes in velocity with respect to time to now an investigation of changes in velocity with respect to where it's at. This is going to be very useful because we find there are certain forces that cause things to move that can be represented as a function of position and not time, which is very useful. For example, gravitational potential energy. This force is kind of a function of position, so to speak, right? And so then there's some very interesting outcomes because of that. Okay, so from here what I'm going to do is I'm going to bring this dx to the left-hand side.
And now we're going to
Yep, that's pretty much it. That's fine. So what we have here is, okay, think back to when we did momentum, okay? What I have here is a force times a change in position. It's kind of like when we did the area under a curve, except now I'm looking at this F net versus position graph. If this graph, as my net force can have any kind of behavior whatsoever, as I'm pushing on an object, right, and it's moving, it's changing position, and I'm pushing on it, and maybe I push it hard and then soft and hard, whatever it is, there is a net contribution of all of that effect, which is what this will represent. that integral represents the summation of my net force over a bunch of little dx-sized rectangles. And I'm just adding them all up. I'm saying as I push on this, my net force is changing, so I need to count it at every single individual moment. And when I add it all up, this is the net effect. And what is the net effect? The net effect is the integral of this one. Now, here I will take a moment to explain the calculation side of an integral a little bit. The meaning of an integral is the area under this curve is the contribution of all these chopped up pieces. The calculation of an integral is simply the antiderivative. The antiderivative, meaning it is the reverse derivative, if you can think of it that way. So if I were to give you, for example, the derivative of some expression equals to x, what would that expression be? What do you take the derivative of to get x?
1/2 x squared.
1/2 x squared. This would have to be 1/2 x squared. If you're not sure about that, try and take the derivative of 1/2 x squared and think about what you get. Okay? The derivative of x squared is 2x. The 2x times the half gives you just x. Right? So this is the integral of x. This is the integral of x dx. Okay, that is the calculation meaning of the or technique, I guess you should say, of the integral. Okay, so when I take the integral of x dx, that gives me 1/2 x squared. If I take the derivative of 1/2 x squared, I get x back. Right? That's kind of the loop. So here in this case, instead of x, I have v. If I assume that the mass doesn't change, then I will have the mass 1/2 v squared. And one other thing that we have to add to it is a little more than just taking the antiderivative. Remember, is the integral is kind of taking up this area, adding it all up from one spot to another. So that means there's some sort of initial spot and some final spot. Okay. Now, the proof of why this works, you'll have to learn that in calc, right? But I'm just saying the technique, what you do, it's kind of like trying to explain to a first grader why you carry the 1. You know, that's just what you do. You wouldn't really, you could try and teach them the meaning behind it. Hopefully you know. It's because we use the decimal number system. But you don't have to know why it works to do it, right? So you don't have to know why you take the antiderivative to do it, but this is what you do. So you will take the antiderivative from the initial value to the final value. Essentially then what you have then is the change in 1/2 mv squared. That is effectively what you get.
What's the rest of it?
Okay?
And then there's another one.
Yeah. There's no plus c if you do from initial to final, right? Plus c is if you have the indefinite integral. Then. Okay. So, has anyone seen this before? 1/2 mv squared. What is that?
It's kinetic energy.
Kinetic energy. So the right-hand side of this is such that you have now derived kinetic energy. If you ever wondered where 1/2 mv squared came from, this is where it comes from. Okay. It is the right-hand side of analyzing Newton's second law with respect to position instead of time. Okay? That is, and it's not just kinetic energy. It's important to note it's the change in kinetic energy. This, the net, the combination of your force pushing on something over a distance, when you add it all up, leads to a change in kinetic energy. But it will never tell you what the original kinetic energy was. You'll notice that kinetic energy, kind of like momentum, is a relative measurement, right? at least as far as classical mechanics goes. Okay, so this is all the right-hand side. So if I were to draw a line, I would draw it right here, because this calculation, all this stuff, that's the right-hand side. It's really important to distinguish the right-hand side from the left-hand side. Just like in Newton's second law, you kind of distinguish the right-hand side from the left-hand side. The left-hand side, you take all your forces, and that will lead to this mass times acceleration. Same thing with momentum. The left-hand side is the sum of your force over a time. That calculation happens on one side, and then the right-hand side is your momentum part. So then lastly here you have your kinetic energy part, but the left-hand side, this is what we call work. This is work. Your work is the sum of your force over a distance. Okay?
I can conceptualize that.
Yeah, I think it's if momentum and impulse, or specifically impulse, is the sum of your force over a certain amount of time, then your work is the sum of your force over a certain distance.
So it's like as if you were doing something and it says, oh, how do you win this spark?
Yes, and so by necessity you must have changed this energy by that much because they're equivalent. Okay, so let's summarize it. You have the work is equal to, or sorry, the net work, the total amount of work done, okay, is equal to the net force added up all over a bunch of little spaces. And that is equal to your change in kinetic energy. This is the work kinetic energy theorem.
Okay, and like what is kinetic energy equal to on one side?
Delta K.
This is a delta K. If you're wondering what K was the 1/2 mv squared.
So let's change the kinetic energy, not just specifically kinetic energy.
No, it is the change. So if you do no net work on an object, you should not be changing its kinetic energy at all. Which means that work is actually more of a measure of a transfer of energy than anything else.
So that's when you can use like heat as like a general definition.
So actually, when you get to, if you ever take a class on thermodynamics, you talk about a total energy equal to a mechanical energy plus an internal energy. You have internal energies being like nuclear, thermal, chemical. You have mechanical energies being elastic, gravitational potential, kinetic.
Stuff looks like bigger.
And then you add it all together, this will have to be constant. If nothing is transferring in or out, right? But this is like the first law of thermodynamics or something like that. It's essentially conservation of energy. But
It's a little bit more involved.
I'll put this in parentheses because not until thermodynamics. Dot, dot, dot. You won't really deal with that until thermodynamics. Although I think it mentions it in the book a little bit. Okay, with a couple minutes left, hold up. There's an important thing to consider about work. Work has to involve a force causing something to actually move. If I push on this book, no matter how hard I push on this book, if it doesn't move, I'm not actually doing any work on the book. Okay? I'm not doing any work on the book because I'm not actually giving it any kinetic energy. I'm not actually transferring any energy to it. So although I'm expending energy doing this, because my muscles, use lactic acid, whatever stuff, it's not actually transferring energy, so there's no work done.
The position is 0, therefore there is no work.
Yes, the position will change. So you must move something in order to actually do work on an object. Okay, so I'll give you a quick example. If I press on a box that's moving this way, and I push on it at an angle, okay, only this component actually does work. This component does no work.
It's lazy.
Does work. Because there's only one component that's actually pushing it in the direction it's moving. So actually, we need to refine our definition of work just a little bit. That if you're looking at the work done by a particular force, not the net work, but for the work done by a particular force, you need to do a dot product. You have to do a dot product. The dot product is how much one vector is parallel to another vector, which means how much they are in line with each other. You're only taking the component that is in line with it. And so this dot products always create scalars, so work is a scalar. Yeah. Yeah. It's a scalar. Even though these two are vectors. Okay, so we'll talk about this one a little more next time. Yeah.